So last time we mentioned a very foundational result of game theory due to von Neumann, and which said that in chess one of these three things are possible, and only one of this is possible. Now in this short module I'm going to prove you, and this will also show the kind of proof techniques that we are going to use in the rest of the course. So just to visualize it as we go along, let us also consider a game tree as we discussed last time. Each vertex in this game tree is a game situation. Now it needs some additional notation. Gamma of x is the subtree that is rooted at x. So the whole subtree, which is starting from here, is denoted by gamma of x. And nx, so this also includes the node itself, and nx is the number of vertices in gamma of x. Now y is a vertex in gamma of x, and y is not equal to x. So let's say somewhere here, as it is shown here. So gamma y is we are going to call as a subtree of gamma x. So this the subtree which is starting from y, we are going to call that as gamma of y, and clearly that is a subtree of gamma of x. Now if nx is equal to 1, that means there exists only one node. This is going to be a terminal vertex. Now the proof will proceed via induction on this nx. Now the theorem clearly holds for nx equal to 1. Why is that? Because if at nx, when there is the terminal node, only three things can happen. Either the white king is removed, in which case b wins. The black king may be removed, in which case white wins. And if both the kings are present and the game ends, then it must be a draw. So it clearly has one of these three strategies, and exactly one of these. Now suppose x is a vertex where nx is more than 1. Now the induction hypothesis will tell me that for all the vertices y, that is in gamma of y, such that the value of ny is smaller than nx, the statement of this theorem holds. So in particular, if we ensure that gamma of y is a subgame of subtree of gamma of x, then also it should hold. Right? This is what we are going to use. Let's consider this part of the network, this part of the tree. So x is sitting here, and the rest of the part is actually gamma of x. Now let's assume, without loss of generality, the white player moves. Even if it's a move for the black player, a very analogous argument can be made, and that can be left as a homework. Now cx, by cx we mean all these nodes, all these vertices that are reachable from x by one move of y, w, the white player. Now we will consider a few cases. The first case is if there exists a y naught, so some y naught here, so let's say this one in cx, such that 1 is true in gamma of y naught. Of course, for y naught, one of the three statements must be true by the induction hypothesis. So let's say 1 is true. What happens? Then we can conclude that 1 is true even in gamma x, for the very simple reason that white can now pick this action, and then for the rest of the thing it can ensure the white to be the winning move. So clearly, if 1 is true in gamma of y naught, then 1 is also true in gamma of x, and we are done. Case 2 is the case where for all the y, so for all the nodes starting from here to here, 2 is true. That is, the black player actually has a winning strategy. Then it is clear that even 2 is true in gamma of x. No matter whichever action the white picks, b will actually look at that action and find out what is its best action in that subtree. So if x picks some action here, it will reach this place, and at that gamma of y, where y is in cx, the best action for black is already known to be. So it will pick that action, and whichever that strategy is, it is going to be a win for player 2, that is the black. Now the case 3 is the most interesting case, where 1 does not hold. So what can we say? So if we just negate the statement of case 1, so for all the vertices, all the game situations in C of X, Y does not have a winning strategy, right? That is the statement. Now, since the induction hypothesis holds for every Y in Cx, either B has a winning strategy or both have a draw guaranteeing strategies, right? That is what it means, the induction hypothesis. Now we come to the second point, that case 3 is also the case where case 2 is not holding. So how do I negate case 2? It means that there exists some Y prime where B does not have a winning strategy. So Y prime is, let's say, in this previous example, there exists some node Y prime where B does not have a winning strategy. So very good, the white knows it, and it can actually pick the action, right? So it can pick that action which brings to this vertex, and because 1 does not hold either, so in Y prime, W still cannot guarantee a win. So all that they can both guarantee is a draw. So therefore W will pick that action to reach Y prime, and B picks the action that guarantees at least a draw. So that is the whole thing, and we are actually done. So this essentially finishes the proof, but this proof actually depends on the finiteness. So we have actually started with the terminal node. The homework exercise that I will leave here is to prove the same result when the length of the game is infinite, when there is no end to it. So please take a look at this exercise 1.3 of the Matchler book, the game theory book, and try to do it yourself.